All right, so we're going to talk today. This is a big day. We're introducing something really very, very important. It's called the fundamental theorem of algebra. Anything called the fundamental theorem of algebra must be pretty important, right? So it's very simple. The fundamental theorem of algebra just says this: if a polynomial has degree n, then it has exactly n complex zeros. Exactly, including multiplicities, right? So if the degree of the polynomial is 5, for example, that's guaranteeing that there are going to be exactly 5 complex zeros. Okay, some of them might have imaginary parts. But if one of those, like let's say one of those, when we factored it, we got an x cubed in there, right? That was one of the factors. Well, then x equals 0. That's the 0 of that factor, right? X cubed equals 0 when x is 0. That one would count as 3 because its multiplicity is 3. So whatever the multiplicity of each 0 is, that 0 counts as that many, okay? For a total of, they have to always add up to n. Does that make sense? We'll get some practice. So along with that, the fundamental theorem, there's a corollary called the complex conjugate root theorem. And what this essentially tells us is that all imaginary roots, and by that I mean complex solutions or complex roots or complex zeros, whatever you want to call them, all complex zeros that have imaginary parts always come in complex conjugate pairs. They come in packets of 2. You can never have an isolated complex solution with an imaginary part. It can't happen. They always come in pairs, okay? So we're going to take advantage of this stuff, and we're going to do the first section is really, it comes kind of in 2 parts. Today we're just going to do some review stuff. We'll come back on Monday and we're going to do some problems where I'm going to give you, for example, like if I told you that this was a 0 and here's another 0 of a function, you've got to build the simplest polynomial that has those zeros. Okay, but that's down the pipe. That's coming Monday. To build up to that, we got to review a little bit, a lot of the stuff that we've already done. So after we put a polynomial equation, if we're going to solve a polynomial equation, we have to put it in standard form first by setting it equal to 0. And then what we're going to end up doing for the next 3 sections in this unit is doing stuff we've already done in the past with just bigger polynomials. To solve polynomial equations, we are always, if they're bigger than quadratic, which ours are pretty much always going to be now, if they're bigger than quadratic, then there really is no magic quadratic formula. There's no cubic formula, right, if it's a cubic polynomial. There's no quartic formula if it's a quartic equation. What we have to do is we have to solve by factoring and the zero product property. That's our only option, okay? So let's review some stuff. Look at this polynomial equation up here. So what's the first thing I have to do? Got to put it in standard form, right? So I'm going to set it equal to 0. I'm going to subtract the 2x and the 14 to the other side, so it's equal to 0. Okay, which gives us that. What's the degree of that polynomial? 2. Okay, good, it's 2. So because it's 2, how many complex solutions are we going to get to that equation? 2, guaranteed, right? So let's get those now. What would I do to solve this one? This is quadratic. You guys can do this in your sleep. What would I do to solve this one the most easily?
You take the 14 to the right side, and then you half of dx.
Okay, that would be tough because b is odd, so we don't want to do that, right? Yeah, we want to always see if we can find magic numbers because that's the easiest way to solve this. Why don't we click them close, please? So we got magic numbers of -7 and +2, which gives us what zeros? Okay, so the 0 of that factor is 7 with a multiplicity of 1. How come it's 1? Okay, yeah, look, the power of that, the exponent attached to that factor is 1. And then the other one is negative 2 with a multiplicity of 1. So if I add those up, I get 2, which is how many I should have. It all worked out. Good? Okay. And if I were to graph this function right here that's set equal to 0, what would I get? Well, how many real zeros do I have? 2. So how many x-intercepts should I have? 2, because real zeros always correspond to x-intercepts, right? So we get x-intercepts at negative 2 and positive 7. Okay, just like we'd expect. Okay, how about this guy? How would I solve that? What am I going to do? X squared minus 4 equals 0. You've done this many, many times. Okay, we could solve by isolating, couldn't we? Right, so we get, if I add the 4 to the other side, I get x squared equals 4. What's the degree of that equation? By the way, this equation 2. Okay, the degree is 2. So how many solutions should I expect to get? 2. Okay, now if I square root both sides, what does that give me? X equals plus or minus 2. So I get 2 and negative 2. What's the multiplicity of each of those and why? 1. How come? You're right. Yeah, okay, because I split an x squared, didn't I? Right? When I square rooted both sides, I know that that has to account for a total of 2 solutions because of that 2, right? And I got 2 separate ones, positive 2 and negative 2. Each has a multiplicity of 1, and so add up to 2. Make sense? Everybody get why we know those are multiplicity 1? Okay? Because this told us we were getting 2. Okay? How about this side? Almost the same problem. What's the only difference? Oh, by the way, and notice here that we get 2 x-intercepts because we had 2 real solutions, right? How about over here? If I solve, what do I get? I can solve by isolating, right? I can point to a single x, okay? And what do I get? Plus or minus 2i, okay? What's the multiplicity of each of those? 1. Is that right? How many should we get? 2. Okay, so it worked. How many x-intercepts? None. How come? Okay, because there are no real zeros, right? Both of the zeros we got were imaginary, so those do not correspond to x-intercepts, right? Only real zeros correspond to x-intercepts. Okay, now, did I tell you a lie? I told you that complex zeros always come in conjugate pairs, complex conjugate pairs. So is plus or minus 2i, does that look like a conjugate pair? A complex conjugate pair should look like this, right? A plus or minus bi. Well, what's b? 2. What's a? 0, right? So it is a complex conjugate pair. We just have to write it with its real part, and then we recognize that as a complex conjugate pair. 0 plus or minus 2i, right? So it does work. I was telling you the truth. About this one. What would I do here? Okay, put it in standard form. I got to push the 4 to the other side. So I get x squared minus 2x minus 5 equals 0. Okay, how can I solve that? Not going to factor, is it? Okay, you're going to complete the square?
No, I'm saying like.
Oh, it should be plus 5. Oh, plus 5. Whoops, there you go. Plus 5. Okay. How could we solve this? Okay, we could complete the square. This is an easy one to do. Or we could quadratic formula this, right? Why is this one a good candidate? Why is it easy to complete the square here? Okay, yeah, so 2 things. A is equal to 1 and B is even. If those two things are true, completing the square is really simple to do, right? Probably quicker and easier than the quadratic formula. So let's review that. X squared minus 2x, I'm going to chase the 5 to the other side. And what am I going to add to both sides? -1 squared, right? Half of b squared. So I'm going to write it, remember, I'm going to write it as -1 quantity squared on the trinomial side. On the other side, I can just write that as a 1, right? Just whatever the simplified number is. How come I wrote it this way? How come I wrote it as -1 squared?
Because it stays the same.
Okay, good, because the number that's attached to the x, the magic number that appears twice, right, is always the number that got squared. So we get x minus 1 quantity squared, right? And on the other side, we just get -4. And so now what? Square root. Okay, so I get x minus 1 equals plus or minus 2i. Last step, add 1. Look at that, complex conjugate pair, just as advertised, right? We get 1 plus 2i and 1 minus 2i. Each has a multiplicity of 1, correct? Okay, for a total of 2, which is what we should get. Okay. And notice the graph has no x-intercepts because there were no real zeros. Okay. All right, let's look at this now. I want you to think about this. Let's just make some predictions here. For a 5th degree polynomial, what is one number of possible real zeros that we could get? 5. Could get 5, couldn't I? I could get, if the degree is 5, the maximum number of real zeros is 5, isn't it? Okay. Okay, if there are 5 real zeros, how many complex zeros are there with imaginary parts? 5? That's not going to work. How come? What's the total number of complex zeros need to be? What's the fundamental theorem tell us? Let's go back. Fundamental theorem of algebra tells us if a polynomial has degree n, then it has exactly n complex roots, including multiplicities, right? Now, are real numbers complex? Yeah, every number is complex, right? Complex numbers is the set of all numbers. Real numbers are complex numbers with 0 imaginary part. Pure imaginary numbers are complex numbers with no real part. And other complex numbers have both a real part and an imaginary part, right? Okay, so if there are 5 real zeros, then how many complex zeros with imaginary parts could there be? What's the total number have to be? 5, so how many could there be? 5 plus 5 is 10. 0, yeah. Right? The total number of real and non-real zeros has to be 5 because n is 5, right? So there are 5, guaranteed. Okay, so I could have no complex zeros with imaginary parts. Just to say that, I'm just going to call them imaginary zeros. That takes a long time to say that, right? Imaginary zeros, when I say that, I'm just meaning zeros that have an imaginary part, okay? What's another, could I have 4 real zeros and 1 imaginary zero? How come? Oh, imaginary zeros come in pairs, right? Complex conjugate pairs. So what's the next possible value of imaginary zeros I could have?
1.
Can't have 1.
2.
2. There we go. 2. Okay. So I could have 2 imaginary zeros, which would leave me with how many real zeros? 3. Okay, that works. What's the other possibility?
4.
4 real zeros, oh, hold on, sorry, 4 complex zeros with imaginary parts, 4 imaginary zeros, and 1 real zero. Okay, so there's no possibility here where I have 0 real zeros. Okay, can you somebody reconcile that with what we know? Now, how would you describe this polynomial if n is 5? It's an odd degree, isn't it, right? So how can we reconcile this table up here with what we know the n behavior is always going to be for an odd degree polynomial? What are the two possibilities for an odd degree? If it's a positive leading coefficient, we get this, don't we? That's positive odd, negative odd. But in both cases, don't I have to cross through the x-axis at least once? Right? If I'm doing this or this, it's got to go through the x-axis, right? At least once. So that means there has to be at least one x-intercept. X-intercepts correspond to real zeros, so doesn't it make sense that there has to be, no matter what, there has to be at least one real zero there for an odd polynomial, okay? Any 1 to 5 on that concept, is that good? Okay. I'm not getting 5s everywhere. Okay. Right, now what does end behavior mean? That means that if I go out to the right forever, this thing is going up to positive infinity in the y direction. If I go out infinitely far to the left, the y value is going down to negative infinity. A polynomial, if I think of it this way, if I graph a polynomial, it's continuous, right? We haven't used that word really in here much at all, if ever. Continuous just means I can graph it without ever picking my pen off the board. All polynomials are continuous. So if I'm going to always leave my pen on the board, and at one end of this polynomial function, I'm going to be down at negative infinity, and the other end, I'm going to be at positive infinity, the y value, and I never pick my pen up, how could I not cross through the x-axis? I have to, don't I? Right? Because the y values are going from negative to positive, or vice versa, if it's negative even behavior, right? No matter what, though, if they're crossing from negative to positive or vice versa, they have to go through 0. Y equals 0. So they must have at least one x-intercept. Okay, how about this one? First step, standard form, so subtract 2. Okay. If I subtract 2, I get x squared minus 2x plus 1 equals 0. Is a factor? What are my magic numbers?
-1 and
-1 and -1. So how would I write that?
x minus 1 squared.
X minus 1 squared equals 0. Okay. All right. So how would I solve that? Square root. That's going to give me x minus 1 equals plus or minus the square root of 0. Well, what's that? 0. Okay. Last step. Add 1. Okay, so I get x equals 1. What's the degree of this polynomial? 2. Okay, and I got x equals 1 is my only 0. Well, how does that work? Because I should, by the fundamental theorem, I've got my zeros have to add up. I have to get 2. How come? What's going on?
Well, that x minus 1 squared.
So what's the multiplicity?
So multiplicity is 2.
2. There you go, right? So the multiplicity, because that's being squared, the multiplicity is 2. So I do get a total of 2, right? Because remember, multiplicities count towards the total, right? Okay, so new issue. How about this one? If I'm going to solve this one, clearly it does not factor, does it? Right? This is a bad candidate for completing the square. So what are we going to do? Quadratic formula. Sure. Okay, so what's the quadratic formula given us here? X equals, which is what? One. Okay. Plus or minus square root. 1, -1 squared is 1. Okay. Minus times 1 times -11, right? All over 2. Okay, so that's giving me 1 plus or minus the square root of 45 all over 2. Everybody agree? Okay. So if I square root of 45 simplifies to what? 3 square root of 5. Okay, so I could, if I want to split this up, then I'm getting x equals 1/2 plus or minus 3 times the square root of 5 over 2. Okay, something else happened here that's similar to that complex conjugate theorem. This is called the irrational root theorem. What this tells us here is that if our polynomial has rational coefficients, if all the coefficients can be written in fractional form, which they can, right? Those are all fractions. 1, -1, and -11 are all rational numbers, aren't they? Okay. If that's true, then if I get 1, 0 of my polynomial that is in this form, a plus b times the square root of c. What that essentially means is if I get an answer that includes a square root that's irrational, right, that doesn't simplify to a whole number, then it has to be part of a pair also. It has to be part of another conjugate pair. This is not a complex conjugate pair, it's just a conjugate pair. But it has to be a part of the conjugate pair a plus b square root of c and a minus b square root of c, right? That's what happened, isn't it? Look, we got this rational term, and then we got this irrational term, so that's like our a, isn't it? That makes sense? Another way of thinking about this is, if we look at our answers, maybe this is easier to visualize. If we get our answers, where our answers are going to look like this, they're going to look like a real term plus, not real, I mean rational, not real. Whoops. If our 0 looks like a rational term, plus an irrational term, and it's irrational because it has a radical in it, then that has to come in a pair where we get the same thing, where the second term, the irrational term, is negative. Okay. Always comes like that. Okay. So it happened here. I got 1/2 plus 3 radical 5 over 2, 3 square root of 5 over 2. So I have to get 1/2 minus 3 square root of 5 over 2. How come? Because I had a square root in there. It has to come in a conjugate pair like that. That's not one that is covered all the time, like in the high school algebra class, but that's a pretty good one. It gives you a lot of insight into the way functions behave. So what are our zeros then? We had 1/2 plus 3 radical 5 over 2 with a multiplicity of 1, and 1/2 minus 3 radical 5 over 2 with a multiplicity of 1. So we get our 2 that we need, because the degree is 2. Okay? All right, one last problem. And actually, no, I'm going to hold off. I don't want to do that until Monday. Back to there. Okay, that's good for today.